Hello everyone, welcome to this video on chapter 7, which is about the explanatory models or the ARIMA models. So the ARIMA models in your textbook are on page number 337. This chapter is all about going through the basic terminology and introduction to the ARIMA models. Then we'll apply ARIMA model to series, and we will close off our topic by going through Young box testing procedure in order to validate the ARIMA model that you have picked for the forecasting. Okay, so in first few slides you will be introduced to the basic terminology associated with ARIMA and other important concepts such as white noise, autocorrelation that you must be aware of when it comes to choosing a correct ARIMA model. So one important note here, when we talk about ARIMA models, we are talking about a large family of models which can be produced by varying autoregressive and moving average components. We'll come to that in a bit more details in coming slides. Okay, so let's come to the three components of ARIMA model. So I stands for integrated component because one of the conditions in ARIMA models is that your time series must be stationary. So in order to make the time series stationary, we're going to take first difference, second difference, or some advanced techniques. So in this particular course, we'll stick to the differencing method. So if you remember from chapter 2, when we take difference for a time series or the first difference, we are removing the trend component. Okay, then we have autoregressive component. So in ARIMA models or the autoregressive component, time series only depends on its past values. So it's like a linear trend. So where we're only using the past values based on some number of lags or the lagged observations to predict the future. In ARIMA, the last term is MA term or the moving average term. So in MA component, instead of using the past observations, a time series will be dependent on the residuals or the error terms, right? Okay, so let's explore these one by one. Okay, so let's go through the terminology and notations used in ARIMA models. The very first thing is the time series must be stationary, so which means no trend, right? In the previous chapters we use first difference to remove the trend components from the time series. We'll use trend component here too. So in order to represent the entire family of ARIMA models, we use three parameters, P, D, and Q. So P represents the number of lagged observations for the autoregressive component. D is the difference that you have used to make time series stationary, and Q is the size of moving average window. So by varying all these three P, D, and Q values, we can create a large family of ARIMA models. For instance, if you're using everything as 0, P equals to 0, D equals to 0, Q equals to 0, in that case we are simply taking the average of the entire time series. None of the components such as autoregressive, integrated, and moving average are playing any role in the forecasting process. Similarly, I can have a value of P equals to 1, no differencing in case the time series is already stationary, and moving average as 0, so 1, 0, 0. Similarly, I can have 1, 1, 0, 1, 0, 1, value of P as 1, D as 0, Q as 1, or value of P as 1, D as 1, Q as 1. So now you can see that we can create infinite number of models by varying the value of P, D, and Q. So that's why in next few slides we're going to use the terminology black box. So we want to determine right combination of P, D, and Q values so that we can reduce the forecasting error. Okay, so let's start with the concept of stationarity, very first thing. So we're going to work GDP data set, which is obtained from Stats Canada. So you already have this data set on Blackboard. So in column A you have date starting from 2000 and as quarterly data, GDP data across Canada, and then in column C we have first difference. So I will come to that in a minute why we have the first difference here. So if you plot this data set and put a trend line, you will see there's a trend going upward. And one of the conditions we have in ARIMA models that we cannot use ARIMA models when data is non-stationary. So we need to transform this data or take the first difference to make it stationary, right? And if you look into the AFC plot or the autocorrelation plot, it is slowly moving towards 0 as we increase the number of lags, from going from 1 to 2 to 3 and up to 12. If you increase up to 24, you will see the autocorrelation will slowly approaches to 0. So we can clearly say there's a trend in this data set. Okay, so in order to keep our assumption of stationarity, we need to transform our data set, right? So there are different ways to do that, but in this particular case for GDP data, as there's only the trend component that needs to be removed from a time series, we're going to use first difference in order to see if we can produce a stationary time series. And as we said earlier, the D will define how many differences you're taken in order to make your time series stationary, and D will belong to I component or the integrated component, right? Okay, so let's make our time series stationary from here. We're going to take first difference. So if we say y dash t is the first difference, is going to be yt minus 1. So let's go back to our Excel document. The first difference for quarter 2 is going to be quarter 2 value minus quarter 1 value, right? Okay. So I will not go into much details on this one because we already applied this in the previous chapters several times, right? And what you're going to do once you have taken the first difference, you're going to plot your time series again, do the autocorrelation. If the first difference doesn't remove the trend, then we're going to go further and take the second difference, and it goes on, right? We're going to take the higher order differencing in order to remove any trend from the time series. Well, usually you will see most of the time series in the real life, you will have either the first difference or the second difference, which removes the overall trend from the time series. So from the assessment viewpoint, you should know why the differencing is important. So you may have some of the complex time series where you have a trend in the variance instead of mean values. We'll not go into much details on this one, but if that is the case, then you're going to take logs of the original time series. Further, you can take the first difference and handle the trend in the time series. The next thing is the autocorrelation and partial autocorrelation. I will not go through details on these two topics because we have already covered these in chapter 2, and here we won't look into these from the application viewpoint. So just to quickly wrap up the autocorrelation and the partial autocorrelation, we're going to say a time series stationary. The value of autocorrelation should diminish rapidly towards 0 as the lag increases. So from our previous slides, this is not the case with the GDP data. We can easily say that there's a trend component in our time series. So we're going to take the first difference to remove the trend, and if trend is removed, it must exhibit this property, right? Okay, so after following the concept of first difference, we took the first difference on GDP data, and if we put a trend line, visually we can say there's no trend in this time series. And further, you can use autocorrelation. So if you do the autocorrelation here, it quickly diminishes towards 0, right, as the lag increases. So the trend component is removed. So that's the idea of differencing and visually inspecting if your time series is stationary or not. So we have looked at I component or the integrated component. In this case, we're going to say that the value of D is going to be 1 because we have only taken the first difference. If we have taken two differences, then the value of D is going to be 2, right? So keep this in mind as we're moving forward. So value of D is going to be 1 for our ARIMA model for the GDP time series. So now further we're going to investigate or look into both plots. The autocorrelation and the partial autocorrelation plots will allow us to determine the right ARIMA model. So one thing you must keep in mind when you're looking at these plots, ACF or the autocorrelation plot will be used to determine the MA component or the moving average, and partial autocorrelation will use to determine the autoregressive component or the AR component. Okay, so before we look into ARIMA models in more details, let's remind ourselves two more important concepts that we have discussed in the previous chapters. So which is looking into the patterns that a time series has, such as trends, seasonality, and so on, and how we're going to use those patterns to generate meaningful forecasts. It simply means picking up a right model to generate the forecast, such as if your time series has trend and seasonality, we applied Winter's model to generate the forecast. Okay, so the next terminology is the black box. Black box is a very broad term, so it's widely used in computer science, data mining, and predictive analytics. Any black box is a model that has certain inputs, and using these inputs, the model produces an output without any knowledge of its internal working. So why we use that term without any knowledge of internal working? Because as we add more variables and your models becomes complex, it's very difficult to understand the interrelationships between those models. So keeping the black box terminology in mind, the overall objective of this process is to find a black box which closely fits to the data. So in order to simplify this, we can use the analogy based on the forecasting models we used in previous chapters. For instance, if you talk about moving average models, so we can say moving average is a black box. The idea is to determine, do I need to use 2 points moving average, 4 points moving average? For a hypothetical example, I can say MA4, or a black box which consists of 4 points moving average, is a better fit if it reduces the forecasting error. All of your regression models that we discussed in the previous chapters have certain inputs such as dummy variables, personal disposable income per capita, interest rate, and so on. So we use all those inputs for a black box, which is multiple causal regression, to produce a time series. So in ARIMA methodology, we're going to use a black box, which simply means ARIMA model, which is going to use some random white noise to produce observed time series instead of explanatory variables. So now the next question is, what is white noise? So let's explore this topic. Okay, so white noise represents a pure random data, which simply means the data has no trend, no seasonality. There's only a random variation in your data set, right? So that takes us back to the idea of removing trend. So if your data set has no seasonality, it has only trend component. Once we have taken the first difference, we have removed the trend component. So which means your time series, or the left time series, is only consists of white noise or the random data. The second important property of white noise is that the previous values do not help in predicting the future values. So this is only possible when you have a pure random data. Okay, so we're going to use the concept of white noise when it comes to validating your ARIMA models or validating the black box. So your ARIMA model is only valid, or is a better fit for a given time series if and only if the remaining residuals or the error terms are white noise. So which means there's no serial correlation between the error terms. So there are two ways to investigate remaining residuals: Young-Buck statistical test and the autocorrelation function, or applying the autocorrelation to the residuals. So we'll look into that by using one example. So here's the kind of standard process how you're going to estimate the black box. So we're going to start with the observed time series. But there are some sub steps that we need to perform. So as we're looking into the ARIMA models, if your time series is not stationary, we need to transform that time series to be stationary first by taking the first difference, right? So once you have your time series that's transformed to be stationary, then we're going to apply the black box. In our case, a particular ARIMA model. It could be ARIMA 111, ARIMA 101, depending upon value of P, D, and Q, right? So that's why we're using the terminology black box, because there are infinite number of models, or the ARIMA models, that you can apply on a time series. But the idea here is, once you apply that model, we need to examine if we are left with the white noise. So which means your residual terms are not serially correlated, right? If we fail this test, which simply means the residuals has some serial correlation, which simply means we didn't pick up a right model to transform our time series. So we need to test a different model. So just to summarize that what we said in the previous slide, we're going to start with a observed time series like GDP data. So in this case, our GDP data is not stationary. So we're going to take the first difference in order to make our GDP data stationary. So once we have our time series stationary, from here we're going to apply a correct ARIMA model, or a correct black box, which means right values of P, D, and Q. And after applying that model, we're going to take the error terms and we're going to check if the error terms are white noise or not. So which means your error terms shouldn't be serially correlated. The errors are only random variation. If that's the case, you got a correct black box or correct ARIMA model. If the errors are serially correlated, we're going to go back to this step again, apply a different ARIMA model. So as I said earlier in the start of this lecture, that we'll be using forecast X. So what I'm interested when it comes to the examination process, you should be able to interpret the results which are generated from forecast X. We will not go through the manual process of applying a correct black box. So we'll stop with the ARIMA terminology at this point, and now let's look into the application part. Okay, so from here we can generate 4 different types of models. Very first model that you're going to have is when there's no differences taken, which means D is 0 as well as value of P is 0. So which means our model only contains the autoregressive component. Similarly, we can have a model which is only based on moving averages, which means again D is 0 and Q is 0. So there's no autoregressive component. The third type of models, you're going to have ARIMA model, no integrative component, in which case your time series is already stationary. So if D is 0, you can have ARIMA, let's say 1 1, ARIMA 2 1, and there are infinite number of possibilities, right? So as we increase the value of P and Q, your model becomes more and more complex. On the final one we have is the ARIMA, in which case we have the integrated component. So I can have a model ARIMA 1 1 1, so which means autoregressive component is present, integrated component is present, and moving average component is present as well, right? Similarly, I can have ARIMA 2 1 1. So similarly, there are lots of possibilities, the different ARIMA models that you're going to have. So let's say you have a model which is written as ARIMA 1 0 0. In this model, we can easily say there's only autoregressive component is present. I can write this model as AR1. So make sure you understand this terminology because you may have some questions around this area. Similarly, if you have another model, let's say ARIMA 0 0 1, this can be written as MA1 because we have autoregressive component absent in this model. So you should be able to differentiate between these models based on this terminology. Okay, so let's look into these components one by one. So just to recap, a moving average model is 1, in which case time series depends on the random error terms. The important keyword here is random error terms, which means the time series depends on white noise, right? So error terms are white noise here. So if you look at this model carefully, I believe this will remind you weighted moving average. So we are not taking a simple average, we're using weights associated with the error terms at a given lag, right? So if we have a model which is MA1, so which is at lag 1, so we're going to have only one weight. If I have MA2, then it's going to be ET plus W1, ET minus 1 plus W2, ET minus 2, and so on, right? So I represents lag, ET error term, and WI is the weight for ith error term. Okay, so how we'll get these weights? We're going to get these weights to forecast X. Okay, so the next question is how we are going to determine the number of lags in MA model. Is it MA1, MA2, MA3? So for that, we're going to use autocorrelation plot. So there's some standard plots that you can rely on to possibly identify the correct model. I'm using term here, possibly correct model. So that's where we're going to look into residuals, and we can use the Youngbox test to make sure you have picked up right model. So from this course viewpoint, there's some plots. I would like you guys to have a careful look at these plots and make sure you understand how these models are associated based on a given plot. I will not ask you to identify autocorrelation or generate a autocorrelation plot, but I will give you autocorrelation plot and will ask you to identify is it MA1, MA2, AR1 or AR2, right? Okay, to sum it up, for moving average, we're going to mainly focus on autocorrelation plot. So in this case, there's only one positive spike, so which means beyond 95% confidence level, So then we can easily say this is MA1 model. Similarly, one negative spike, that should be corrected here. It is not positive, negative spike. And if that's the case, your partial autocorrelation plot gradually oscillates to 0, right? So that's going to give you MA1 model 2. Similarly, if you have two spikes, it's MA2 model, and here again two negative spikes is MA2 model. I'll not read through this, so have a look at these patterns and make sure you understand these. Okay, so the second type of models in the ARIMA family are the autoregressive models. If you look at the autoregressive model equation, it looks very similar to the moving average equation, but the only difference here is that instead of using the residuals, we are using the historical data. So the time series depends on its historical values, right? So again, here AI is the weight for the ith term, and YT minus 1, T minus 2 are the historical time series values. So the next question is, like pure MA model, how are we going to identify, is it AR1, is it AR2, AR3, and so on. So for MA model, we relied on the autocorrelation plot. However, for the AR models, we're going to rely on partial autocorrelation plots. So one positive spike beyond 95% confidence level, and you're expecting the rest of the spikes within 95% confidence interval, right? Okay, next, so if you have one spike, one negative spike outside 95% confidence level, and the autocorrelation function gradually oscillates to 0, then it's AR1 model. Two positive spikes beyond 95% confidence level, rest you're expecting within the 95% confidence level, are AR2 model. And finally, you have another two spikes beyond 95% confidence level, and autocorrelation plot gradually oscillates to 0. So again, as I said, for the AR models, please make sure you look at these patterns carefully. The third type of model in the ARIMA family are the ARIMA models, so where we are only using the autoregressive and moving average component. In this case, no integrated component, which means your time series is already stationary. We are not transforming the time series. If you look carefully at the equations, so we are using the equations which were derived in the AR and MA models in the previous slides. So here your time series will be generated, which is combination of the historical values, or the YT, plus the residuals, or the white noise, right? So again, going back to the black box analogy, so depending on your time series, you may have ARIMA 1.1, ARIMA 1.2, ARIMA 1.3, ARIMA 2.1, 2.2, 2.3, and so on. There are infinite possibilities to have different ARIMA models, right? Okay, so the next question is, how we're going to identify how many lags we require for a particular ARIMA model. Is it going to be ARIMA 1.1, 1.2, 2.1, and so on? So we're going to look into the, again, autocorrelation, partial autocorrelation. So here's some standard plots that you're expecting for ARIMA 1.1 model. So if it's ARIMA 1.1 model, you're expecting that the autocorrelation and the partial autocorrelation are gradually oscillating towards 0. So again, going back to my previous comment, so please have a look at these plots, and you're expecting a autocorrelation and partial autocorrelation plot in your exam, and I may ask you to identify correct ARIMA, AR, or MA model, right? Okay, so this brings us to the Box-Jenkins identification process. So as we are walking through Box-Jenkins identification process explanation, please make sure you keep this diagram in mind, right? So that you know which step we are at. The very first step is going to be examining the raw data, right? The first question you should be asking, is the raw time series stationary, right? So if not, we're going to take the first difference to make the time series stationary. So once you have checked that, then we'll start with step number 1, which is the identification process. So in the identification step, we're going to produce autocorrelation and partial autocorrelation on the raw data. So what I would like you guys to do, you have the GDP data set, plot a correlation and autocorrelation using forecast X, and that will allow you to identify a tentative model. So the term we are using here, tentative model, this is not confirmed model at the moment. We can only confirm this model once we have went through the validation process. So for the first step, give it a go. Look at the partial autocorrelation and autocorrelation plot to identify the value of P and Q. We already know the value of D is going to be 1. Our time series has a trend. We need to take one first order difference. So here's some explanation how you're going to identify the model. So I'm expecting that after looking at the autocorrelation, partial autocorrelation plot, you will conclude that the value of Q equals to 0 and value of P equals to 1. So which means you're going to have ARIMA 1, 1, 0. Value of P as 1, D as 1, and Q as 0. The next step is to identify the parameters or the weights for the AR and MA component. Anyway, in this case, the MA component is 0. We're not using MA. We are going to end up having ARIMA 1, 1, 0. But for the AR component, we need to identify the weights or the weight for the first lag. So for that, we're going to use forecast X. So the third step is the diagnosis process or the validation of the ARIMA model to ensure that we have chosen the correct model. So for that, we're going to look into Young-Buck statistics test. So don't worry about this equation on QM. So this equation is that if anybody wants to explore further how the QM values are calculated. However, we are going to get these values from the forecast X. But make sure you keep in mind how the degrees of freedoms are calculated. So degrees of freedom are equals to number of time lags to be tested. So if it's quarterly data, we're going to use time lag 4. If it's monthly data, you're going to use time lag 12. There are some special cases where you have seasonality. We may end up using time lag 48, but we'll not explore that. At this point, you can stick to time lag 4 and time lag 12. Then value of P the number of lags for the autoregressive model, and Q, number of lags for moving average model. Make sure you look into value of P, Q, and M in order to get the correct degrees of freedom. So here are the results after applying ARIMA model through forecast X on GDP data. So one quick note here. So the idea of first difference was only shown to walk you through the process of ARIMA model. So when you're using ARIMA through forecast X, you don't need to take first order difference. Forecast X will take care of this. Because whenever you select any model in forecast X, we can always uncheck the edit parameters. So which simply means let forecast X optimize the value of P, D, and Q for you, right? So we have ARIMA 100, so which means the value of P is 1. We're using 1 lag for the autoregressive term. So the second parameter's value of D is 1. Why that is 1? Because we know that there's a trend in our data set, so which means we need to take one first order difference, and value of Q equals to 0. So as I said earlier, do the autocorrelation plot and try to compare what tentative model you're coming up with. I'm expecting that you will have 1, 1, 0. And from here, the weight for the autoregressive term is 8.37. So you can complete the AR equation from here in case I ask you to write the AR equation. So I'm just going to quickly take this back to the slide where we have the AR equation. So I'm going to end up with the autoregressive model, which is going to be AR1. A1 is 8.37, the weight we have from the forecast X, YT minus 1 plus ET, right? So that's the equation using AR term. Okay, so let's get back to the results. The next one is the Young-Buck statistics that we got from forecast X. So this is the QM value, which is 5.53. So again, we're going to use a standard procedure to validate our results. So our standard procedure starts with getting the Young-Buck test statistics results from forecast X. We already have that. So once we got the QM values, calculated values for the Young-Buck test statistics from forecast X, we are going to apply or perform a chi-square test, in which case we're going to establish a null hypothesis, which is the model doesn't exhibit lack of fit, which means your residuals are white noise. The residuals are independent, right? An alternative hypothesis is going to be the residuals are not independent. There's a serial correlation between residuals. When that happens, your model exhibits lack of fit. If you want to draw a conclusion based on this, H0 simply means you have selected a correct ARIMA model. H1, your ARIMA model is not correct. That's why there's a lack of fit. So once you establish the hypothesis, then we're going to get the chi-square values from the chi-square distribution table. So how are we reading this? So here's the chi-square, and we're working with 1 minus alpha. So if the confidence interval is not given, it's going to be 0.05, and degrees of freedom. So degrees of freedom, we already know that. So you have formula for degrees of freedom, which is m minus p minus q, right? So in our case, degrees of freedom are going to be 3 because value of m is 4, as we are using 4 lags as correlate data, and value of p is 1 as autoregressive model, and moving average model is 0, right? So we fail to reject null hypothesis if the calculated value is less than the critical value or the table value. So let's apply this based on what we got. So we have calculated value at 4 lags 5.33. we already have degrees of freedom as 3. So from here we're going to get the chi-square values from the distribution table. So you already have the distribution table provided at Blackboard. So at 3 degrees of freedom we have value as 7.815, right? Okay, so let's go back to our slides. So which means we fail to reject null hypothesis because a calculated value at lag 4 is less than the table value, right? So it simply means the correct ARIMA model is selected. The residuals exhibit white noise. So the residual terms are independent. There's no serial correlation between the residual terms. So similar to this, you should be able to conclude in your exam if the right ARIMA model is selected or not. So that concludes our young box test statistics. We have only looked into one method when it comes to identifying if you have selected right model or not. That concludes the ARIMA chapter. So as you have noticed that we didn't go to the seasonality part, and we simply walked through the introduction to the ARIMA models, and as I highlighted that you should be able to apply chi-square test based on given output generated through forecast X, and you should be able to read the autocorrelation and partial autocorrelation plots. So spend some time on that. If you have any questions, feel free to reach me out.